by Dr. Ben Cumming, who is a group lead in the Scientific Software and Libraries Unit at the Swiss National Supercomputing Center, CSCS. Ben? I think you're muted, Ben.
Okay. So yeah, thanks very much, Samir and Mike, for the opportunity to present at the forum today. As we said, I'm from the Swiss National Supercomputing Center, and I want to talk today about practical performance portability, which really means, in my language, approaches to performance portability for software that we have found have worked in our experience at our CSCS. So I can't really speak directly about the extreme scale, software stack, which is the main topic of this forum, because we're not really directly involved with that yet. But it does really look like a fantastic initiative. It's really well aligned with a lot of the things we're trying to achieve with our next, system that we're going to be installing at CSCS. But I do have some things to say about, approaches for ensuring that scientific application and library components in this software stack are performance portable. I'm presenting, most of the work that I'm presenting here is it's the hard work of our talented developers at CSCS. This is an opinionated talk, so it's meant to be a conversation starter, and the opinions are entirely my own. So I want to start with a little bit about CSCS's motivation to really work on performance portability. And we were one of the very early adopters of GPU technology, motivated by the limits that we saw coming for CPU scaling in the face of power limitations, and the market forces, which are often much larger than the HPC community. In the case of GPUs, video games, and now the nascent AI industry. So in 2013, we installed our flagship system, Piz Daint, which was a GPU-based system. We're one of the very first national centers to go all in on GPUs. And at the time, it was number 3 in the top 500, which is a very big investment for a little country like Switzerland with a population of about 7 million people. And we then upgraded in 2016, and it's still in the top 10 today, but it's still a GPU-based system. At the same time, and the first project that I worked on in my time at CSCS was working with the Swiss National Weather Service, Meteo Swiss, to port their operational weather forecasting code to run fully on GPUs. And the result was a system that we installed in 2016 that was the first national weather system in the world to use GPUs for operational weather forecasts. And just this year, we've installed a replacement system for that, which is again based on GPUs. So that's been a great success story for us. So we've been very interested in how do we get our user program, very motivated to get our user program, who at the time, when we first installed Piz Daint, had applications that had been optimized and tuned to run mainly on the Intel platform, which had been dominating for the last 10 years. But Piz Daint's getting a bit old, and in 21, 22, we're going to be looking to replace it. And now we've got even more choices. As Mike pointed out, we're going from a single GPU vendor in NVIDIA to a whole ecosystem of different types of GPUs and accelerators. So we can see that this, the rest of the HPC world has caught up, and more of the power, the computational power in your top leadership systems are all getting their speed up from some form of acceleration. And not only that, but the heterogeneity of the accelerators is also increasing. We've got NVIDIA, AMD, and in the near future, Intel GPUs, as well as other kind of hybrid platforms like the AE64FX Fujitsu ARM CPUs. So I want to start by kind of defining what is performance portability. And in the way I view it, there's two key requirements. The first is performance, and that means we achieve effective, efficient execution on the supported architectures. So if it says it runs on Intel CPUs, then it should vectorize properly and make efficient use of caches. If it's running on a GPU, it should fully overlap, host device computation and communication, and really get, a significant proportion of performance. And a key point here is that this is always going to require some amount of target-specific code for your key algorithmic motifs. I've never seen a complicated or reasonably, production-ready portable application that didn't have at least some of the specific code paths for specific architectures optimized. People often stop there when they think about performance portability, but I think portability really means not only does it run on the different supported architectures, but the effort required to add support for new architectures should be reasonable. Now, the definition of reasonable really is quite subjective, and it depends on the application. If you have a huge monolithic Fortran weather forecasting application with hundreds of stencils which have been written, handwritten into for loops, a reasonable amount of effort to port that to be to a new architecture is actually going to be that's going to be quite a lot of effort. It's probably not that portable. So this requires really effective isolation of the target specific code, so that changes to target specific code or adding new targets doesn't affect the rest of the software stack. So I've got this, so the approach for portability is really separation of concerns. I've got this rather complicated looking diagram here, which I think is complicated because no two applications or libraries or domains are the same, and the different approaches you might use to finally achieve, portability are going to be different across these different applications. But the key idea here is that at some point you're going to have an interface that separates the domain-specific scientific part of the application from the specific hardware targets and optimize bits of code for the different architectures. And this should be quite a clean interface, which really does talk the language or domain-specific language and doesn't let the architecture leak into the rest of the application. So we have had a strong focus on CUDA. It's not our only focus. We've been putting a lot of effort into AMD HIP and ARM SVE porting over the last 6 months or 12 months. But CUDA has been our main focus because we've been using NVIDIA-based GPUs for the last 7 years. But if we look at some of our code bases, so I've got 4 of the applications we work on here. They're all open source applications and they're all available on GitHub. And if you go to GitHub and you look at this little infographic they display showing the proportion of the different programming languages, we see that in all of these cases, the amount of CUDA code is between 0 to 3% of the code, and it's usually less than the amount of lines of code in the CMake or config-based installation tools. So I think this kind of shows that if the target specific code doesn't necessarily have to be a large chunk of the code if things are done right. So to achieve performance portability, it does require significant upfront refactoring costs. What those costs are going to be really depends on the nature of the application and how it's been written and the nature of the domain and the algorithms. But I think these refactoring costs are worth it if they improve the long-term maintainability and long-term portability of the applications and libraries. And I'm going to talk about 2 specific ways to do this. The first is to kind of separate the front-end scientific domain part of the code from the hardware abstraction via domain-specific APIs. And the second is when people using the software need to actually specify algorithms or key parts that need to be specialized and run on different architectures, we can use domain-specific languages and code generation so that users can write this domain-specific part once and then have code generated for the different backends. And both of these have a common theme of separating the science or the domain descriptions from the hardware or architectures underneath them. And I think the best way to explain these rather vague things is to actually look at some case studies. So these are all applications, or more specifically libraries, that we've been working on at CSCS. The first is called Sirius, and it's a C++ based library that's been developed for the Quantum Espresso application. Quantum Espresso is a very large, very important application. It's an ab initio quantum chemistry method. I should say it's a very important application for CSCS because it runs a lot on our system. It's a Fortran application that uses MPI and OpenMP, and it makes heavy use of BLAS, LAPACK, and FFT. These really are the main the numerical workhorses in this library. And the key challenge here is, how do we port all of the different diverse methods and algorithms that it implements in a way that uses a common set of domain-specific motifs? So when we started this project about 4 or 5 years ago, and we looked at different options. We initially looked at the option of intercepting calls to the BLAS, LAPACK, FFT and just substituting in the GPU accelerated equivalents. But that wasn't going to work because the cost of constantly copying information backwards and forwards between host and device was going to be too much. So we needed a more significant refactoring where we really did move more of the work onto the GPU. The first option was to work directly on the Fortran code using OpenACC or OpenMP 4.5. At the time, OpenMP 4.5 was the most recent version of OpenMP. This still would require a large refactoring of Quantum Espresso. And a key point here is, even if you use OpenACC or OpenMP, you're not going to get performance portability for free. We've always found when we use these directives-based approaches that we end up having multiple versions of each loop with the directives on them, with tweaked changes for specific target architectures, or even for different GPUs from the same vendor. At the time, OpenMP wasn't really proven in production, and I don't know how widely used it is today for accelerator offload workloads. And a final important point is that it's very difficult to hire ambitious young developers to work on Fortran. There's not that many of them. So the approach we took was to rewrite the basic DFT building blocks in a standalone library, which we present with the domain-specific API, and then do some refactoring inside Quantum Espresso, the Fortran application, to call into this library. So the result was the library called Sirius, which is in the middle here, which you can think of as a domain-specific language because its interface is strictly in terms of the domain. So users interact with it in terms of DFT ground states, geometries, K-points, bands, and Hamiltonians. Now, these things don't make an awful lot of sense to me. I'm not a solid-state physicist, but there's no mention of the underlying hardware there. One benefit of this approach is that we're using Sirius today, not only in Quantum Espresso, but in other applications, including our CP2K, which we've also heavily involved in the development of. And then underneath all of that, we've wrapped and hidden away all of the different, target-specific libraries and bits of code that we had to write to support all these different architectures. And you can see we've got CUDA, ROCm, and then generic different CPU architectures supported. This has given us very good performance portability on Piz Daint, our main system. We've just got some benchmark results here. I won't go into any detail here. We don't have that much time, but they show that we get very good performance on the GPU. And more importantly, we're able to effectively utilize the GPUs on Piz Daint. So at the moment, CSCS is maintaining a version of Quantum Espresso that we have refactored like this, and that we always keep up to date with master. And it currently has support for Intel vectorized CPUs and other CPUs, which have got optimized math libraries, as well as NVIDIA GPUs and AMD GPUs. And the effort, once we'd put all this in, the time it took to add the AMD support was not very big, because we already had support for CUDA and other backends. The Quantum Espresso developers also have their own CUDA Fortran version, which gets good performance. It's comparable to the Quantum Espresso Sirius version, but it does support less features than Quantum Espresso Sirius, and it does have a portability problem. It's now got 2 versions of everything, and I don't think CUDA Fortran is going to be portable to other architectures in the near future. So this library is, I think, a good example of creating a domain-specific interface so that you don't have to change most of the domain-specific part of the calling application and then having the specialization in the back end. Our second study is a library called DBCSR. I'm just going to check for questions. I can't see any questions, so I'll keep going. So DBCSR is a sparse linear algebra backend for a piece of software called CP2K, which is another quantum chemistry application. And this is one of the main users on Piz Daint as well. And the main algorithmic motif here is distributed sparse matrix multiplication. So very, very large sparse matrices distributed over MPI. And the key feature or twist with these matrices is that the sparsity, the dense or the non-sparse parts are small, dense block matrices with dimensions that we don't know until we actually instantiate a model and start running a model. So we can have a wide range of different little block matrix sizes. So doing the multiplication, we need to be able to multiply many different small matrices together. And this was refactored quite a long time ago by the CP2K developers, who realized that if they wanted to add GPU support, they decided that the best way to do that would be to split this off into a separate library. The GPU backend collects many of these small dense block multiplications together and then ships them off to the GPU in an efficient way. And then it uses these highly parameterized little matrix multiplication kernels written in CUDA. So the challenge with these little matrix multiplications is that the exact set of parameters that you use, like the amount of shared memory, the amount of registers, the number of warps, this sort of very GPU specific information really depends on the size of the matrices, and it's very hard to tell a priori what the best, the optimal parameters are. So the approach in the past was to basically auto-tune the parameters ahead of time for many, many different matrix dimensions and generate some kernels and compile them all into one big binary. That had a problem that the auto-tuning consumed a lot of resources. It meant that we had a very large binary for all of, so we ended up having to form the CPU when an appropriate kernel wasn't available. So we took the approach recently of jitting these kernels at runtime. So making a best guess when auto-tuned parameters were unavailable. And the big challenge here was, how do we pick optimal parameters for each target GPU? Because every time we got a new NVIDIA GPU, so if we go from Pascal to Volta, we had to redo this auto-tuning process. And the approach that we settled on, which was very successful, was to use some simple machine learning to determine the JIT parameters. So we would first perform some auto-tuning to generate a set of training data of optimal parameters. And then we created a little regression tree based model and trained that to generate, so that we would be able to infer parameters when we didn't have auto-tuning information available. And this was very successful. The predicted, the parameters that we were able to predict were usually about 3%, within 3% of the auto-tuned kernels on average. So this was a big success. So this means we have to do much less auto-tuning on each new GPU architecture. And then we have a much faster compilation process as well. So as a result, the CUDA backend for this took years to develop and tune, because there was a certain upfront cost that had to be paid in building the first new backend for this library. We also have a backend that is maintained by Intel, that works on Intel CPUs. When our young software engineer, when she went to add the AMD HIP port, I asked her to keep a diary and record how much time she spent on it. And it took her 21 days to get it fully up and working and running and tested. Because we have code generation, we didn't have a ton of, a whole stack of CUDA kernels to port by hand. We just had to train the code that writes the kernels. We had to do some wrapping of API calls to make it more generic, not just CUDA, but also HIP specific. And there was something that we find we always spend a lot of time on, and that is wrangling our CMake and auto building tools to work with the ROCm toolchain. Adding a SYCL one API backend would take longer because SYCL has a different syntax to CUDA, but it would only be in the order of a few months, I think, because the programming model of SYCL is the same, or very, very similar to CUDA, because it turns out that CUDA is a very good programming model for targeting GPUs by virtue of being designed for GPUs. So there was a large initial investment in developing this DBCSR library and splitting it out from the main Fortran application. But as a result, we've shown that we can adapt to new accelerators more easily, and CP2K will be running on the biggest systems in 10 years' time, which is not bad for a legacy Fortran application. So we don't necessarily advocate for getting rid of Fortran applications, but we advocate for carefully targeting how we do the refactoring. Final application I want to look at is a library called Arbor. So Arbor is a C++ library for the simulation of networks of multi-compartment neurons, and it's been developed from scratch in Europe over the last 5 years as part of the Human Brain Project. And the main challenge we have here in this application or in this domain is that scientists want to be able to define arbitrary ion channel and synapse models, which they then want to distribute on their arbitrary cell shapes. And I always like to use this, this historical picture of a Purkinje cell. It's one of the more complicated or most complicated neurons in the brain, to show the possible complexity that you can have to deal with here. And people want to define their synapses and ion channel models and distribute them over something like this. But the other cell types in the brain have got a completely different shape and completely different properties. And the problem here is that these ion channel and synapse models are exactly the things we want to be running on our accelerator. So how do we facilitate scientists being able to do this? The first step we took when designing the library was to make sure that there was a clear separation between the model descriptions, which we call recipes, and the context, which is our hardware description. So never should we have a recipe or a model description include anything about hardware. It should be a pure domain-specific description. And then we have a clear API, where we take these two things, combine them to build a simulation state, which presents a nice uniform interface, C++ API or wrapped Python API to our users. And then if we go all the way down into the back end, we've got the specialized CPU and GPU implementations of these different things, of the different dynamics, as well as different backends for MPI and thread parallel communication that can be selected, that are basically set by the hardware description. The main challenge is that there are two real constraints on portability for us. And these are driven by that, that efficient ion channel and synapse computation requires that we have hardware-specific optimized implementation. And our users want to be able to define their own arbitrary mechanisms, ion channels and synapses, and run them. And the main challenge is that it's not practical to explicitly implement optimized code for each possible mechanism or ask our users to do that. And the solution is fairly obvious in the end, is to use a domain-specific language where the user writes down a mathematical description of their dynamics. And then we have a compilation or transpiler that takes this and can generate optimized target-specific code for each of our different target platforms. So we have this domain-specific language, and we compile it for 3 different targets. At the moment, we've got a generic, naive C++ CPU code that relies on compiler auto-vectorization. We also have a target, which is a C++ vectorization library that currently has support for AVX2, AVX512, ARM Neon, and recently added ARM SVE specializations. If we want to add support for a new CPU architecture, we just need to provide a new specialization, which doesn't require touching anything else in the code. Of course, we don't live in a perfect world, and recently when we did the ARM SVE backend, we did have to make some changes to this vectorization API because SVE, as you know, is a bit different from other vectorization approaches, and it did break some of our assumptions, but it still didn't touch anything else in the rest of the code, the rest of the software stack, you could call it. We also have a CUDA and ROCm GPU backend. So we added the ROCm AMD support very recently, based off of our existing CUDA backend. And again, this took about 2 weeks for one developer. And that work involved first testing our CUDA backend, whether we could compile it with Clang, because we found in a lot of our projects that if you can compile a CUDA kernel and get it to run well using Clang, then it'll run quite nicely with ROCm, because the HipCC compiler is also Clang-based. Then writing the various backend specific glue and helper code, and then spending way too much time messing around with CMake to support the ROCm toolchain, which is partly CMake's fault. And then iterate on our existing unit and integration tests. So we've been very fussy about maintaining comprehensive unit tests, and this really paid off. Once we had the unit test passing, everything just worked. So I'll quickly conclude now. The take-home message is that, for real performance portability, it's worth paying the upfront cost to refactor interfaces and use code generation so that the scientific part of your application or models doesn't have to be rewritten for each new backend or target architecture. And I've got a quick observation here that, achieving portability is going to require engineers and developers. Even if you decide that the approaches I've talked about here aren't worth it and you're just going to go and completely rewrite a Fortran application, that's going to require that is going to require manpower to do that. And computer science programs at universities aren't producing many Fortran programmers. I think that's an understatement. But they are producing many smart young developers who are familiar with or are really motivated to learn things like C++, LLVM, MLIR, and domain-specific language design. And they're also very motivated to contribute to science. So these happen to be the skills that are required to increase performance portability in our codes. So this is a slightly outdated picture of our team. Our team has now grown, but we're basically, at CSCS, we've hired 30 people, professional developers, to work on developing the software. And we've got a nice mix of our older guys like myself and then young masters and PhD graduates who amaze me every day with how resourceful and clever they can be. And on that note, I will finish the talk and ask if anyone has any questions.
Hi, Ben, there are some questions in the chat window.
Okay, one moment. Okay. Did that actually work for you guys, the HIP stuff? Yes, it did. We were particularly successful when we stopped trying to use, I forget, there were always two compilers, one which was based on a fork of Clang and one which was much closer to Clang. When we stopped trying to use the fork and we tried to use the Clang-based compiler that is going to soon be upstreamed into the mainline Clang, that worked for us. Can
I ask a follow-up question on that?
Yep, so one final thing there. The tool chain is definitely a bit immature. It's like AMD are trying to basically build the train whilst it rolls down the tracks, catching up with the CUDA stack. But yeah, I've been working on more recent versions of the ROCm stack and it's getting more stable all the time. But yes, it is a little bit.
What was your initial CUDA code based on? Which CUDA version did you still support?
I suppose most of us have moved to CUDA 9. Aarbor recently moved to CUDA 10.
Okay. Yeah, because we're running in so many compiler bugs. I mean, we're just getting stuck like all over the place all the time. Even the latest. No.
Okay, well, you can definitely get in touch with us. We've ported nearly all of our large applications to run, and they run fast. They run optimally on the AMD GPUs. So we've had great success. So yeah, get in touch.
So Ben, this is Hari from the Ohio State. I had a question about the AMD ecosystem. So we ran into some issues with compiler optimization and HIP memcopy. where the data was not appearing in the device buffers post hit memcopy without an actual touch. Did you also encounter this?
Haven't encountered that one specifically. As I said, there have been lots of little bugs and gremlins in the tool chain, but I think that's improving a lot. We've been having much less hassle with each new generation of the ARM GPU. So I hope that by the time they're actually installed in the systems we depend on, it works. See, I've got a question here. C++ develops rapidly. Do you mostly rely on a subset close to C? No. We are upgrading most of our projects to C++ 17 at the moment, and we don't rely on that subset close to C. We like to use the nice new features that make our programs safer and easier to maintain.
Then there's some more questions.
Yeah, one other question in the chat.
Oh, okay. What's the skill set mix of your team? I don't know what an RSE is.
Research software engineer.
Yeah, so these are research software engineers. So they're not PhDs or master students who have got other priorities or projects to work on. They are hired solely to do this work. And we're very lucky at ETH that we're able to produce. We've got a computer science and engineering program that basically produces people who've got the right mix of math and C++ and HPC experience. I know this is one of the biggest challenges, but we're kind of lucky that we're situated right next to a source of these young guys where we can grab them for a few years before they go to work for Google, basically. But we've been able to tempt them by telling them that by getting them to work on interesting C++ projects and staying in science.
Well, thank you very much, Ben. Really appreciate your talk.